Welcome to our 10th Inspiration Exchange session. My name is Nick Maxfield. I handle the Schaar Lab's communications, and I'll be moderating today's session. I'm also joined by Mihaela and Alihan Hüyük, who will be giving presentations and handling our participative discussion today. So first, to give you an idea of what to expect from today's session, as always, our ongoing aim with Inspiration Exchange is to share and explore the breadth of topics in machine learning for healthcare and to generate new ideas for future research. Our previous two sessions, our 8th and 9th session, were kind of deep dives on individualized treatment effect inference, or ITE inference. I highly recommend giving these a look on our YouTube channels, since this is a very, very important area at the intersection of machine learning and healthcare. But today we're very excited to do something completely different and introduce quantitative epistemology, which is an entirely new field of research pioneered by our lab, the aim of which is to use AI and machine learning to understand and empower human learning and decision-making. But to break this session down for you time-wise, we'll kick off with about 15-minute to 20-minute introduction and overview by Mihaela, which will be kind of a high-level introduction to quantitative epistemology in general. And then we'll have a roughly 25-minute presentation by Alihan Hüyük, who is one of our Ph.D. students. And he'll be presenting some more kind of in-depth approaches and frameworks. And then we will go into a participative discussion or Q&A on quantitative epistemology. And this can be on the area in general, or it can also be on something specific that you've seen in one of the presentations. So what I'd like to encourage you to do is post your questions into the Inspiration Exchange Slack channel. And if you don't know what I'm talking about, please just have a look at one of the previous emails that I've sent you about this upcoming session and just follow the link in that. So basically what you'll do is post your questions into the Slack channel. The earlier you can do that, the better, because it gives us a chance to list up the presentations, the questions during the presentation, and then we can kind of think of our responses. So you don't have to just ask your questions during the Q&A session. Actually, doing that earlier is much better for us. And then once we're done with the discussion and Q&A, we'll go into some closing words and wrap up after just about 1 hour. Before we get started with the presentations, I just wanted to point you towards one of the resources you can find on this topic on our website. So basically, if you just visit our website and you go to Research Pillars, and there's a drop-down menu, you just click Quantitative Epistemology. And what this is basically a fairly broad overview that goes a little bit into the theory and framework for this area of study, as well as some of the potential applications, some of the work we've done so far, the intersections with other areas of study, and of course the path ahead, since again this is a very new area of study and we do plan to build on it. So please do visit our website to check that out. But next up, we have a roughly 15 to 20-minute presentation by Mihaela. And again, if at any point there's anything you want to ask a question about, please post it straight away into the Inspiration Exchange Slack channel so we can see it and kind of prepare to answer your question. Okay, and Mihaela, if you wouldn't mind sharing your screen, and please take it away.
Thank you very much, Nick. Wonderful. Okay. So thank you very much, everyone. And thank you so much for joining us. I'm really happy and excited to be talking today about an endeavor that we have pursued over the past 2 years. And this endeavor is called quantitative epistemology. And we believe that is a new field of research, which is very important piece and step in conceiving a new partnership between man and machine. I'd like to start by explaining the name. I'd like to start by first describing what epistemology is. For the ones among you who may not know, that's the study of knowledge. And it is the knowledge that humans can acquire that we are going to focus on. Quantitative is really referring to things that can be measured. So this is why quantitative epistemology. How are we going to go towards quantitative epistemology. Today, we are having conventional decision-making analysis using machine learning. And the focus is very much to replace humans or to guide humans, or at times even to outperform humans. And fields such as optimal control, operations research, reinforcement learning, apprenticeship learning, imitation learning are all parts of this agenda. We have gone beyond this and looked at a different agenda, which is going to be described by Alihan and me in quite some detail, which we call inverse decision modeling. And the focus of this agenda is to understand humans, to understand, explain, and audit decisions, to give quantitative accounts of past behavior, to identify variation in policies and identify potentially suboptimal behavior, inclusively the triggers for this suboptimal behavior, whether it's biases of different kinds, or the fact that the humans may forget to take certain information into account, or may take into account information too late, and also ways to improve policies. But the long-term agenda will go one step further. And what we are aiming to do in quantitative epistemology is to create a true partnership between human and machine. And the focus really is on empowering rather than replacing humans. What do we plan to do here? Help humans acquire better information, direct them towards the right information to consider at a particular moment in time, help them evaluate diverse sources of information and turn them into decisions, learn various ways in which humans represent knowledge and create actionable information for them to be able to build new knowledge and acquire new knowledge, as well as do new discoveries. Identify ways in which the internal knowledge models of a human are constructed and are evolving over time, and provide best ways for humans to learn and acquire new knowledge. But also this may empower humans to communicate better and more effectively with each other, thereby adding rather than replacing human communication. All these different areas come alive not only in healthcare. We are going in the duration of the talk today, give several examples from healthcare where the humans are going to be clinicians or patients. But the reality is that this research agenda in inverse decision modeling and the longer term agenda on quantitative epistemology are not only going to empower the medical profession and patients. This is also going to be useful in many other areas, in finance, economics, accounting, criminal justice, education, etc. So the standard machine learning agenda today very often envisions a scenario where there is no human agency. All the decisions are made by machines, by machine learning engines. And I'm showing here an example from some of our own work on machine learning for healthcare. But as I mentioned before, this goes beyond medicine. And often machine learning is envisioned as being empowered by humans and how they make decisions today. So often there is a discussion on machine learning 2.0, where people are trying to use insights from humans and how they make decisions and learn to empower machines. So in machine learning 2.0, often insights, for instance, from Nobel Prize winner Daniel Kahneman are considered, and the system 1 and system 2 that he describes in his book are considered as ways that can guide machine learning engines to learn more effectively and make better decisions. So the focus is incorporating the design of our human-like AI and ML to empower ML. So the focus is very much on replacing and outperforming humans. Another machine learning agenda, maybe more friendly to humans, is that of standard decision support, where machine learning can provide guidance and recommendations to humans, whether it's in healthcare, where a particular type of diagnosis or a particular type of treatment is suggested. And machine learning, especially reinforcement learning, as well as other branches of machine learning, have played an important role in this area to guide human decision-making. But what we want to do is to go in a different direction. And this is why our lab over the past several years has worked on the first step towards quantitative epistemology has been inverse decision modeling. And Alihan will talk later in more details about exactly this framework. And inverse decision modeling is focusing on understanding humans, trying to understand why they make decisions, based on what information they make these decisions. Often decisions, for instance, in medicine are based on complex information that's integrated over time by the decision maker. So trying to analyze the sources of information, as well as analyze past behavior, why a particular clinician has behaved in a particular way at this moment in time, and why has he or she treated differently a seemingly similar patient in the past. Understand variation in decisions, both by the same decision maker, but also by multiple decision makers, as well as identify suboptimal behavior. Why certain, for instance, clinicians may have better outcomes for their patients than other clinicians. Is there something systematic that they do worse or they do better? Are there biases? Are there systematic mistakes, etc.? The long-term agenda, though, is going beyond inverse decision modeling. And quantitative epistemology thinks about partnering with humans and empowering humans, thereby building a new partnership between human and machine. And the focus of this is extracting actionable meaning from analysis of decision-making. By, for instance, understanding the root causes of variation in practices, understanding biases, building internal models for each individual, trying to understand how knowledge is acquired and evolving over time. Flagging in use of information, potentially what type of information should be considered or disregarded at a particular moment in time. Trying to identify new ways to learn, and as well as facilitate communication between humans. Currently, for instance, in the clinical domain, you may have multiple clinicians discussing with each other on behalf of the patient, and often they may use quite vague language. We may have, with quantitative epistemology, enabling these two clinicians to communicate more precisely and more effectively on behalf of their patient by pointing out the exact sources of information they have used when making certain decisions, or highlighting why they believe that the prognosis of the patient would be such if a particular treatment or intervention is given. So we are also in this way creating an empowering loop for the humans to maximize their potential and help them make better decisions, as well as learn more effectively. So this feedback loop enables us to use knowledge about how we learn and make decisions to help us learn and make better decisions. So unlike existing work, for instance, in standard decision support, where the black box model will learn something from data and then is trying to turn the black box into a white box by just trying to interpret the predictions of the model, in this case, we are going in a totally different direction. We are trying to understand, using machine learning, the decision-making of the human, present it to themselves, and enable them to use this information to better themselves, improve themselves, better interact with other humans, as well as build tools using machine learning as well as other methodologies to empower them. Also, this is not useful for just the decision makers. It's also useful for the researcher, because this type of loop can create new hypotheses and discoveries. For instance, we may identify that certain clinicians are treating patients at a particular moment in time and in a particular way, which is more effective than others. And this may lead to new hypotheses and discoveries which researchers can consider and then can inform subsequent decisions. So thereby further empowering the whole human-machine ecosystem. Let me also highlight the differences by showing how decision support systems, as we currently have them, are going to change in the future with quantitative epistemology. So if we think about decision support today, decision makers are provided with support which enables them, for instance, to detect mistakes, maybe mistakes in diagnosis or, for instance, treatment in the case of medical settings, or by enabling them to predict outcomes or outcomes over time. And this type of recommendation is often done before making a decision. In quantitative epistemology, we have a totally new ecosystem. For instance, the decision makers, clinicians or patients, will be provided with information that can enable them not only to detect one-time mistake, but also systematic errors, validate intended decisions, become more aware of different sources of information and how this is integrated over time, avoid biases and cognitive biases of all kinds. But also maybe to some of the decision makers, training may be recommended because their decisions are no longer up to date and new sources of information and new sources of new, for instance, medications or new ways of treating patients may become in effect. So in this way, we are not only learning and creating this man-machine ecosystem at one time, at decision time, but we do this continuously. The same happens for stakeholders. And by stakeholders, we envision here, for instance, in the case of healthcare, it could be the hospital owners or the stakeholders in the healthcare system. For instance, in this case, we may try to understand variation in practice. We may want to understand reasoning behind a particular decision, why a particular treatment has been made. And also we may want to ensure that the decision is indeed right, and we cannot make more cost-effective and more patient, and we cannot improve patient outcomes through different decisions. So this can be done after a decision is made as well as continuously in order to improve the performance of, again, man-machine interaction. Another area that this is true also for supervisor managers, policy makers, which may use this type of tools to assess current practices and understand new policies, when new policies will come in effect. Currently, for instance, in medicine, clinical practice guidelines are often established quite late. And only after a few years of consensus, a new guidance comes in effect. This type of human-machine ecosystem could allow identifying better new practices more effectively and measuring the impact of new policies as well as existing policies continuously. We believe that quantitative epistemology can be also very important for trainers and teachers, and we strongly believe in continuous learning using machine learning. We can find best ways to represent information and knowledge, and what are the most effective ways for a particular individual to be taught a particular concept and enable them through continuous learning. But also we are in this way able to identify from other humans what has worked for them in learning on mastering new skills and provide it as support for a person that is just about to start to train themselves in this new skill. Finally, researchers, as I mentioned before, can analyze this behavioral data, form hypotheses, and contribute to decision-making theory. And this is both during the scientific process as well as after data collection and before experimentation. Alihan will talk more about this later. So what have we done in the last 2 years since we started this research agenda? So we have worked on a variety of preliminary works so far that are providing insights in this quantitative epistemology path. First, we have looked at how timely is the agent decision-making, and here by an agent, I mean a human. What reward function does the agent optimize? What type of performance metric is the agent having in mind? Then, how important are various counterfactuals in making decisions? What are the subjective beliefs of the agent? How optimal is agent behavior relative to an ideal behavior, an ideal reward function? And do we deal with bounded rationality? And how does agent behavior evolve over time? All of that is encapsulated in a paper that we are going to present at ICML 2021, and which Alihan is going to present a little bit later, which is the inverse decision modeling framework, which is a very powerful model that encapsulates almost all the works we have done so far. And if it is to contrast with what the current state of machine learning is, where the focus is again on replacing and outperforming humans, work in behavioral cloning, imitation learning, inverse reinforcement learning. Unlike all these works, we are going one step further because the focus is really on understanding humans, both the way in which they deal with knowledge uncertainty, decision-making complexity, specification complexity, and recognition complexity. And part of this agenda will be presented by Alihan next when he talks about inverse bounded rational control within the framework of inverse decision modeling. But in order to further this agenda, we are going to need to develop new machine learning models beyond what we are going to describe to you today. Just two of the main areas that are going to empower this framework are planning strategies, whether it is operation research, control, etc., where we need new models as described by us, as developed by us in the last 2 years, but also going beyond, as well as new learning strategies. And indeed, in the inverse decision modeling framework, we needed to innovate on both these two regards. But if it is to go really towards a new human-machine partnership through quantitative epistemology, we need a whole new set of machine learning tools. So we believe that machine learning will play an important role in this, creating this partnership. But for that, we need to think beyond the current methods and the current solutions developed in machine learning. So we believe that this is also a true opportunity for machine learning researchers. So to finalize, we are very excited about this new research field that we are trying to build because it will enable us to create a new human-machine partnership. And this is useful not only in medicine, but generally when humans need to make complex decisions in expert environments. Also, we believe that this is a new field of multidisciplinary research, where machine learning will need to join forces with other areas of research in operations research, economics, behavioral economics, cognitive research, psychology, etc. But we do believe that machine learning researchers have a lot to contribute in this area, and new machine learning methodology is required. And the steps that we have made along the way, as Alihan is going to show to you, are going to highlight the need for new thinking. Finally, I'd like to emphasize that the reason we are so excited about this new area is that we depart from the current thinking of the machine learners who focus on replacement of humans. We rather want to empower humans and create a new partnership. Thank you very much.
Great. So next up, we have Alihan's presentation, which, as I mentioned, will be about 25 minutes, and he'll go into a bit more depth about some specific approaches and models and frameworks. Again, if you do have any questions, please post them into the Slack workspace or the Slack channel, Inspiration Exchange, and you can find the URL for that in my previous emails about this session. Thank you.
Hi everyone, my name is Alihan and I'm a PhD student in Professor Van der Schaaf's group. Today I'm going to present you some of the work we have done on quantitative epistemology. I will start with Interpretable, which is one of our early work on understanding behavior. Thinking about how Interpretable fits into existing ways of analyzing decision-making led us to developing inverse decision modeling, which is an even more general framework for understanding behavior. I will present this framework next. And finally, I will talk about inverse bounded rational control to illustrate how inverse decision modeling is useful in formalizing new ways of analyzing decision making. So first up, interpretable policy learning, or Interpol for short. Our objective in this work is to obtain a transparent understanding of human decision making, and we do so by learning interpretable representations of demonstrated behavior. As a motivating application of this goal, consider the significant regional and institutional variation that exists in medical practice, which happens to be the leading cause of rising healthcare costs. Having a more systematic understanding of medical practice would be the necessary first step to reduce this variation. Note that this objective is unique from other endeavors in decision-making analysis, where the most common objectives are either to replicate decision-making behavior, as in imitation learning, or matching the performance of an expert decision maker, as in apprenticeship learning. When tackling it, we keep three key criteria in mind. Most importantly, we want to learn representations that are transparent by design. But we also require our method to accommodate partial observability and to operate in a completely offline fashion. Since in most real-world environments, including healthcare, observations are partial in nature and it is impossible to experiment online freely. We propose Interpol, which is the first policy learning method to satisfy all three of our key criteria. As our problem setup, we consider decision-making environments where an agent interacts with their environment in discrete time steps. At each step, the agent makes an observation that is partially informative of their environment and takes an action on the basis of all their past observations according to some behavior policy. In doing so, they generate a dataset of demonstrations that consist of action-observation trajectories. Then, the question we ask is how to obtain an interpretable parameterization of the agent's policy solely from the demonstrations they generate. Interpol is one such parameterization. It models policies in two distinct stages, through decision dynamics, which describe how available information is accumulated as belief states from one time step to another, and through decision boundaries, which describe how those belief states are then mapped into individual actions. Given a state space readily understood by domain experts, for instance in healthcare this state space could be the progression stages of a disease, past observations can be summarized in the form of beliefs, which are essentially posterior distributions over the unobserved states. We will model how beliefs are updated from one time step to another as a Bayesian update that is carried out according to some internal model of the environment's dynamics, which we call decision dynamics. It is important to note here that these decision dynamics are subjective to the agent, and they do not necessarily need to match the true dynamics of the environment that dictate how observations are emitted on the basis of actions. The figure shows how a belief update might look like for a three-state environment where the triangle represents the belief space. Once a belief is obtained, we parameterize how it is then mapped into an action through individual mean vectors for each action, such that the action whose corresponding mean vector is closest to the current belief is most likely to be chosen by the agent. Intuitively, this induces some decision boundaries and regions over the belief space as shown in the figure. Having introduced a parameterization for policies, our learning objective is simple to determine the quantities that form decision dynamics and decision boundaries, given demonstrations. Following a Bayesian approach, this can be achieved via expectation maximization by maximizing action and observation likelihoods jointly. To illustrate how our method could be useful in understanding behavior, we consider the decision-making problem of ordering or not ordering an MRI during the diagnosis of Alzheimer's disease. While an MRI is often informative of Alzheimer's, it is also financially costly. Alzheimer's progresses in 3 stages: normal function, mild cognitive impairment, and dementia, which constitute our state space. And as observations, we consider cognitive test results and MRI outcomes of patients. Here are decision trajectories for 2 typical patients from the ETNE dataset. Each point in these diagrams corresponds to an individual visit to the hospital, and it represents the clinician's subjective belief regarding their patient's underlying state during that visit. The closer a point is to one of the corners, it means the more confident the clinician is about their belief. For instance, if a point were to be directly on top of the corner corresponding to dementia, it would correspond to an absolute certainty of dementia being the true underlying state. We see that the first patient is believed to remain around the decision boundary, and appropriately, they are ordered an MRI during approximately half of their visits. The second patient, on the other hand, is believed to be deteriorating from cognitive impairment toward dementia. Hence, they are prescribed an MRI in all their visits. In this next example, we use Interpol to detect a patient who appears to have been diagnosed later than what should have been possible. Note that the patient was not ordered an MRI until their third visit, although a typical patient would have been ordered one. Once an MRI was finally ordered, it led to near certainty of mild cognitive impairment, which could have potentially been known significantly earlier. Overall, 6.5% of all ADNI patients were subject to a similar pattern. We can also use Interpol to quantify the value of a test in terms of its information. While this patient was ordered an MRI in all of their visits, it may appear on a surface level that the third and final MRIs were redundant, since they had little to no apparent effect on beliefs. However, this is only true for the factual belief update that occurred according to the MRI outcome that was actually observed. In the counterfactual, these MRIs could have potentially caused drastic leaps towards MCI if the outcome were to be different, meaning the MRIs were actually highly informative. In fact, this particular patient happened to have had cognitive test scores that were suggestive of impairment. So it might be the case that clinicians were using MRIs to eliminate the very likely possibility of impairment and make sure their patient was still functioning normally. To evaluate how interpretable Interpol really is compared with alternatives, we have consulted 9 clinicians from 4 different countries. We first asked them their preferred way of representing a patient's medical history. All 9 clinicians preferred belief trajectories obtained using decision dynamics over tabular representations. We then asked them their preferred way of representing decision-making policies. 7 out of 9 clinicians preferred the representation in terms of decision boundaries over the one offered by a reward function. In conclusion, interpretable representations of behavior provided by Interpol enable auditing, quantifying, and understanding human decision-making processes. Having introduced Interpol, now I'm going to talk about inverse decision modeling, which is an even more general framework for understanding behavior. In fact, Interpol can be thought of as an instance of inverse decision modeling. Our motivation in this work is the fact that human decision-making is not always perfect, mainly due to boundaries of human rationality and the cognitive biases they have. When this is the case, we then ask the question, how can we help humans make better decisions? Of course, correcting any imperfection human decision-making might suffer from, first requires identifying those imperfections in a quantitative manner. In order to address this need, we propose inverse decision modeling. It is essentially a framework for learning interpretable representations of decision-making behavior. Importantly, it enables us to describe existing behavior of an agent relative to what we might consider as ideal behavior. This in turn makes it possible for us to identify the imperfections we aim to address. In order to see how inverse decision modeling achieves that, first consider the conventional ways of analyzing decision making. The forward problem is concerned with what constitutes ideal behavior. It starts with some sort of task representation. For instance, in the standard reinforcement learning setup, this task representation could be a reward function that we want to maximize. Then, it outputs the optimal behavior that best achieves the represented task. The inverse problem, on the other hand, aims to describe what the existing behavior looks like. It starts with the behavior itself and works backwards to obtain a representation that explains how that behavior has come to be. Solutions for neither problem offer much help to us. While forward solutions ignore nuances of human behavior completely, inverse solutions mostly focus on imitating human behavior rather than improving it. Inverse decision modeling is a type of inverse analysis that infers a representation from the existing behavior as well. But in order to do so, it leverages solutions to the forward problem as a theoretical benchmark. We refer to the particular forward solution considered as our normative ideal. Essentially, it describes what we think is the best way to solve the decision-making problem at hand. Since the behavior representation obtained by inverse decision modeling is given with respect to this normative ideal, we can easily use it to generate prescriptive advice for humans that would guide them toward our normative ideal. This advice could come in the form of new guidelines, for instance. On the basis of this new advice and new guidelines, the existing behavior would of course change, after which we can use IDM again to infer a representation of that new behavior and issue new advice. This way, we can keep improving human behavior in a feedback cycle. We start by considering the standard decision-making setup. Here, at each time step, the agent is in some internal state Z, and on the basis of this internal state, they take an action according to some decision policy. Then, their action causes the environment to transition into a new external state S, and emit an observation that is indicative of this new external state. Finally, the agent updates their internal state on the basis of that observation according to some recognition policy. We refer to any information that is relevant to the agent in planning their behavior as the planning parameters. For instance, in the standard reinforcement learning setup, the utility function that the agent aims to maximize would be a planning parameter. We also refer to the distribution of actions and observations induced by the agent's policies as the agent's behavior. Then, a forward planner aims to find the behavior that would optimize an objective determined by a given set of planning parameters. Again, in the standard reinforcement learning setup, that objective could be the expected cumulative utility. Now suppose we are given demonstrations of the agent's existing behavior. Moreover, suppose we partition the planning parameters into a normative and a descriptive part. Then, an inverse planner aims to find the descriptive part of the planning parameters given the normative part, such that the behavior induced by the two is as close as possible to the demonstrated behavior. A better way to conceptualize this operation is to think of it as the projection of the demonstrated behavior onto the space of behaviors that all satisfy the same normative standards. And in our framework, those normative standards are specified in the form of a forward planner and a fixed set of normative planning parameters. What we have been calling as inverse decision modeling is essentially this projection operation. This formulation not only subsumes a wide range of existing algorithms, but it also opens up new possibilities for interpretive research on decision-making behavior. In order to see how, consider inverse reinforcement learning within the IDM framework. There, the forward planner is the standard reinforcement learning planner, and we have no normative parameters. In turn, we seek to infer the utility function of the agent as our descriptive parameter. Essentially, inverse reinforcement learning asks the question, what would be the utility function that the agent maximizes if they were indeed maximizing a reward function? Using IDM, we can ask even more interesting questions than that. For instance, Suppose we already know a utility function that we consider to be optimal. We might want to investigate how rational an agent appears to be in pursuing that ideal utility function. Here, the ideal utility function would be a normative parameter that we specify rather than a descriptive parameter that we infer. Instead, our descriptive parameters would be the various measures of rationality that we can come up with. In fact, we investigate this question even further and develop what we call inverse rational bounded control. This requires us to first describe a bounded rational planner as part of our normative specification. We will assume that the agent has uncertain knowledge of their environment, which is given as a prior or the transition and emission dynamics. However, we will allow the agent to deviate from this prior based on their internal state according to some specification policy. Assuming that the agent would have performed Bayesian inference as their recognition policy if they were to know their environment perfectly, the overall recognition of the agent could be described as an aggregate of such inferences weighted according to their specification policy. Then, the bounded rational planner aims to maximize the expected cumulative utility, much like the standard reinforcement learning planner, but with additional constraints on how much the agent's decision, specification, and recognition policies can deviate from some pre-specified priors. Motivation behind these constraints is that human rationality is similarly bounded. Solving that optimization problem leads us to a value iteration rule that is familiar from reinforcement learning, except with additional complexity terms discouraging deviations from prior decision, specification, and recognition policies. We take how freely the agent can deviate from the prior decision policy as a measure of their flexibility, how freely they can deviate from the prior specification policy as a measure of their optimism, and how freely they can deviate from the prior recognition policy as a measure of their adaptivity. In order to see the impact of flexibility, optimism, and adaptivity on behavior, we consider a simple environment for medical diagnosis. In this environment, patients are either disease negative or disease positive, and vital sign measurements taken every step noisily indicate the patient's underlying disease state. Then, the decision clinicians need to make is whether to keep monitoring a patient and collect more evidence for a diagnosis, or to stop and declare a final diagnosis that is also either negative or positive. Our normative specification of the utility function is such that correct diagnoses are awarded 10 utility, while incorrect diagnoses are awarded minus 36, and it costs -1 to monitor the patient for another time step. In this first figure, we see the effect of flexibility on behavior. Here, the x-axis represents the clinician's subjective posterior over their patients through disease state, and the red markers show how that posterior is updated as more positive observations are made. In both cases, when the clinicians are a little bit more than 80% confident in their diagnosis, they are more likely to stop monitoring the patient and declare a final diagnosis. However, the actions of the inflexible agent is much more stochastic compared with the very flexible agent. This is related to the concept of behavioral inconsistency in psychology. In the next figure, we see the effect of optimism on behavior. While the optimistic agent believes observations to be much more informative than they actually are, and update their subjective posterior accordingly, the pessimistic agent believes them to be less informative. This is related to the phenomena of over and under reaction. In the final figure, we see the effect of adaptivity on behavior. The non-adaptive agent requires less evidence before they declare a final diagnosis compared with the adaptive agent. This is related to the concepts of base rate neglect and confirmation bias. Now that we have described the bounded rational planner, we can return back to our original question. How rational does an agent appear to be in pursuing an ideal utility function? We can formulate inverse bounded rational control as an instance of IDM to answer this question. Our forward planner would be the bounded rational planner we have just defined. Our normative parameter would be the utility function that we consider to be ideal given the decision-making problem we analyze. And our descriptive parameters would be the measures of flexibility, optimism, and adaptivity we have just discussed. As an example case, we are indeed able to infer how flexible an agent is using inverse bounded rational control. Next, we tackle a more challenging task. First, notice how non-adaptive and optimistic behaviors are very similar to each other from the perspective of an outside observer. Both agents declare a final diagnosis after making only 2 observations, which is earlier than what a perfectly rational agent would do. However, while non-adaptive agent behaves this way due to their confirmation bias, the optimistic agent behaves the same way due to overreaction to new evidence. Inferring adaptivity and optimism parameters together using inverse bounded rational control, we are able to differentiate the 2 types of behavior despite their apparent similarities. On the other hand, making the same distinction using inverse reinforcement learning is not possible. If we try to infer the effective utility function of the agent as if they are behaving perfectly rational, we get pretty much the same result for both cases. The inferred utility functions punish incorrect diagnosis less than our normative specification of -36, which is consistent with non-adaptive and optimistic agents declaring diagnosis earlier than ideal. However, we are not able to identify the underlying reason behind such behavior. As a more realistic task, we consider the diagnosis of Alzheimer's disease using a real-world dataset. Here, the decision-making problem is to determine when to order an MRI during the diagnostic process and when not to. Note that MRIs are often informative of Alzheimer's, but they are also costly. First, we recover the optimism parameter for all patients at once. Then, we do the same thing for different subgroups of patients. We see that clinicians appear to be significantly less optimistic when diagnosing patients with the APOE4 genetic risk factor, female patients, and patients over the age of 75, which also happen to be the patients who are at more risk of Alzheimer's. Here are our group's other work conceptualized within the IDM framework. We have already talked about Interpol and IBRC in detail. Besides those 2, we have also looked into timeliness in decision making, which required us to formalize the forward problem of timely active sensing, much like how we have formalized bounded rational control in this presentation. In April, we have developed a new inverse planner for the more conventional problem of inverse reinforcement learning. In CIRL, we have investigated the role of counterfactuals in decision making in a causal framework. And finally, in ICB, we have worked on giving interpretable accounts of past behavior and how it evolved over time. In the short term, future work could include coming up with different parameter structures within the IDM framework for different interpretive goals, very much like what we have been doing within our group so far. A longer-term agenda could be to investigate how representations learned by a framework like IDM could be used to advance our understanding of how humans behave and our theory of human behavior, beyond just analyzing decision-making at a surface level. I have mentioned how IDM can support a feedback cycle where advice informs behavior and new behavior informs new advice. In the future, a similar framework could help us generate new hypotheses regarding the mechanisms behind human decision-making. Once such hypotheses eventually turn into new scientific knowledge, they can inform our normative ideals in turn, which could lead us to generate even more nuanced hypotheses. Again, this process can continue in a loop and help us refine our theory of human behavior continuously. Thank you for your attention.
All right, lovely. So now it is time for our Q&A session and discussion. So our questions are all happening in our Slack channel. as I mentioned, and we actually have quite a lot of them lined up now, which is fantastic. We can probably take one or two more. So just a quick note, I think we were planning to end the session on the hour, but I think we can extend maybe 10 minutes or so that we can get through some of these fantastic questions that we've got. So what will happen is when it's time for you to ask your question, we'll ask you to unmute yourself, at which point please unmute yourself and specify basically which topic you're talking about. And we would like to try and build in about 1 minute, if possible, per question, and probably a total of 2 minutes per question and answer combination. And while the question's being answered, or once you've asked your question and it's been answered, please remember to remute yourself so we don't continue to hear you kind of throughout the rest of the session. So I think our first question is from Max Chen. So Max, if you want to go ahead.
Yeah, well, thank you everyone for the interesting presentations. So I just have a quick question. When we keep saying continuously learning, did you mean, for example, using the decision we learned as new observational data and put it in the training data set? And how do we evaluate this decision other than using the estimated reward we learned for this particular decision? And do we actually execute this decision and wait for the result? Or what if that's impossible, that's impractical to actually execute this action? Thank you.
So thank you very much, Max, for this question. So I think that we envision both types of embodiments. An embodiment like you envision, where eventually the model, so let's say the quantitative epistemology engine is going to take into consideration online the feedback and the decision of the human, and is going to maybe retrain a particular model to better support the human in subsequent decisions. So that's a possibility. Of course, that would require building a quite complex system that will need training and retraining online. When I was mentioning in my part of the talk continuous learning as opposed to just one-time learning, the idea was more that we have already trained on the basis of observational data sets that we already have, all different types of behavior from one individual, but potentially other related individuals. So then at runtime for a new individual, we are going to be able to use this wealth of experiences to identify where this particular individual may need support and show to them alternative decisions that are made, potentially on the basis of alternative information, and enable hence this decision maker to see different types of scenarios. And as this person is making decisions, new things are going to be presented to them. I didn't necessarily envision that the entire model, for instance, the inverse decision model, would need to be retrained in each step. But of course, you can envision scenarios where this could happen as well. Alihan, would you like to add maybe anything to this? This is such a good question.
Yeah, I think I will add only a minor thing. Part of the question was that is reward functions that are learned our only way to kind of evaluate the behavior we are observing? And the answer to that would be no. For instance, like in inverse bounded relational control, we have come up with all sorts of measures for evaluating how irrational someone might be that are quite independent from the reward, like that are distinct from reward function estimation. And in the future, what IDM enables is to come up with even more metrics like this that can be more actionable than like a simple reward function estimate.
Okay, thank you very much. That was very inspiring. Thank you.
Yeah, okay. So I think our next question is from Bernard. Bernard, if you'd like to unmute yourself and ask away, that would be great. Sorry, Bernard, I don't know if you're trying to ask your question, but you may be on mute, or maybe it might be an issue with your microphone.
Can you guys hear me now?
Yeah, brilliant. Thank you.
Okay, sorry about that.
No problem.
I don't quite know what I'm doing. But yeah, I think this is super interesting, and this could be for either of you. But I was just wondering what other types of theoretical or applied models of decision making you might see as future directions for quantitative epistemology. I guess reinforcement learning, or kind of adaptations of reinforcement learning, is kind of a very natural framework, and it really makes sense. But what would be some other approaches that you could foresee as future directions for research? I don't know the answer to this, obviously, but yeah, I don't know if there are representations of knowledge through graphs or other things that you see could be a direction here.
Alihan, you are muted. Maybe you go first.
Yeah, thank you very much for that question. So in fact, what we want to do with quantitative epistemology is to challenge this reinforcement learning dominance as the only kind of way of making decisions, like in the machine learning literature. And so far I didn't present them now, but so far we have looked into, for example, decision trees as an alternative to reinforcement learning, as a way of describing decisions. Now we are looking more into preferences of humans and how they might kind of motivate their decisions. And yeah, I guess the point is very much we are not happy with the current state of machine learning in like considering reinforcement learning is the only way of describing decisions, and this kind of frameworks like IDM allows us to make careful assumptions about that and then challenge that a little bit. And there is surely more ways to consider. And yeah.
If you allow me to just very briefly, since I like the question very much. So we also have looked in some work such as Schaar Lab at counterfactuals as a way of making decisions. And as Alihan rightly said, what potentially we find also as interesting is different humans may have different models for integrating information over time, and potentially arriving at decisions. So we even would like to explore these different representations as a way to empower the human to make more effective decisions, but also humans to collaborate. So this is when I was talking about human collaboration and better human communication, allow these different mental models that maybe different individuals may have to coexist and allow them to have a dialogue, but a more quantitative dialogue than just language itself would allow. But again, this is, I guess, the research agenda.
Yeah, great. Thank you so much.
Okay, lovely. So I think next up we have Alize. And Alize, I think you actually had two questions. And if we could ask you to just sort of split them so that one of them is a little bit later in the list. So that I think the first one that you asked was about learning. I hope that's not so broad that you don't recognize it.
Yeah, sure. So my question was, as kind of a challenge that I see in learning from observational data, because we don't necessarily want to interact and play around with the policies, so we have to learn from observational data. And how do you think we could deal with the challenges that come with this? For instance, making sure that we learn causal relationships from the data, and that we're not learning that because a patient hasn't had previous treatment, they are healthy, but more kind of the correct decision-making policies that go through the physician's brain.
Yeah, that is actually a very important point, because whenever we come up with a model for how someone is behaving, it is just that it's a model, and the reality will certainly differ a lot from that. Like, for instance, certainly when a human is making decisions, they're not thinking about reward functions and value functions and stuff like that that we like to talk about. The reality is much different from that. But what our methods kind of enable us to do is to take them to a like simpler framework that we can tweak and kind of reason with. And one advantage of IDM as opposed to more kind of traditional machine learning is that our methods do not necessarily require trust from the user, because whatever explanation we gave about the behavior might as well be completely wrong, and it's kind of the next step would be on the user to kind of explore that hypothesis and see how valid it actually is. Whereas something like a decision support system, more like at the moment, demands the trust of the user about conclusions it came up to it. So kind of IDM has advantages in that regard. And again, to emphasize again, these models are kind of just models. It's one possible explanation, not necessarily the true explanation. Yeah.
Great. So I don't know, Mihaela, if there's anything you want to add. Otherwise, I'll just move on to the next
I would
question.
like to.
Okay.
Sorry.
Go ahead. Sorry.
I'd like to, because this is such a great question. So another thing is, of course, one could think, Alice, about a situation where there is an interaction and a dialogue. So maybe in the future, there will be multiple explanations provided by the machine. Let's say, are you thinking in this way or that way? And maybe the humans can select their own preferred way of interacting with this machine that is becoming now their supporter and their debugger and their empowerment. And different people may use different ways to interact and may find different ways to represent their thoughts, whether it is a causal graph, whether it's a decision tree, whether there is some of this other framework that Alihan was showing, or maybe some new ones that they can bring in. So I think one could even envision a scenario where user models could be provided, where a user itself provides its own model or builds in their own model. And within that framework, one can learn. So, or one may graduate among models, possibly.
Super interesting. Thank you very much.
Okay, great. So I think our next question is from Evgeny, and probably best for Alihan, but maybe also Mihaela, you might want to add something. Please go ahead, Evgeny.
My question is, so could there perhaps be scenarios where the humans are actually utilizing some information, some additional information to make their decisions, which isn't necessarily available in the data set that we're using? And so how can we handle that type of situation in the context of quantitative epistemology?
Yeah, so I think none of the work we have done so far directly addresses this, but certainly in the future, one could imagine a system that kind of detects inconsistencies in behavior, and kind of that could have been caused by some external reason. And at that point, as like Mihaela said, in a future system that is more in chat with the user, we can directly ask the user, okay, I like these things do not seem to be consistent according to the information I have. What you were thinking when kind of making decision, why the difference? So we can actually, with a system like that, discover this kind of not recorded factors that come into behavior. And it could be really important because some of these factors could actually be irrelevant to the decision that is being made. For example, we do not necessarily want a doctor to decide on a treatment based on how somebody looks, which wouldn't be on the data. And it would be great if you could detect those inconsistencies.
Yeah, makes sense.
Yeah, so thank you, Evgeny, for the great question, and thank you, Alihan, for the answer. Let me also just very briefly say that to some extent, there is a whole of discussion about confounders and confounders in the data, hidden confounders in the data, when we talk about topics such as causal inference, like we did before. Now, with this type of framework, we have an opportunity to go back to the person and say, have you made these decisions on the basis of these factors, or was there more? Because currently clinicians, for instance, since we talk about the clinical setting as an example, but I assume in other professional settings, this would be true as well, they say a lot of things about the patient and then kind of what factors they took into consideration when making a particular decision. Now, of course, they may have forgotten something important. So this is a wonderful way to debug that type of note-taking as well, such that in the future we make sure that if the doctor, for instance, had something into consideration that maybe didn't put in the note, but actually was in their mind, they make this explicit. And this is important for discovery. This is important for integrating decisions, for understanding variation in practice, for discovering new things. So I think it's a very, very important point.
Thank you.
Okay, I think we have another really good question from Alize again. This one's on uncertainty. Alize, if you want to go ahead and unmute.
Sure.
Thank you.
Yeah. The other question I had was how we could try to think about separating all of the sources of uncertainty that the policy model we have in the end gives us. So I was thinking, I mean, a really interesting source of uncertainty would be to highlight the physician's uncertainty in the decision making, but there's also other sources such as variation in practice or even just the uncertainty in the model, that it might be quite hard to separate all these sources. So I don't know if that's something you've thought about.
Definitely, that's actually a very good point. And one type of variation that was particularly interesting to me that you already mentioned is that is one thing that an individual doctor is kind of inconsistent with their actions, but there's also could be this like more high level variation in that individual, like different doctors are not inconsistent in terms of their policies. And at least in healthcare, variation that occurs in terms of like variation usually is unwanted, especially in healthcare situations, because like you don't want to get different treatment across different hospitals, for instance. And it is certainly important to detect those type of variation and in particular differentiate it from variations of an individual doctor's actions. And the first step we try to take towards is that Interpol is actually learns in a Bayesian framework. So all the results I showed were for the maximum of posterior estimate, but one can also look how, for example, the decision boundaries I draw varies within the data. And that would be separate from like the action probabilities that are already baked into the Interpol model. So that could be one, like the first step to kind of differentiate the two. But I think it is such an important problem that like more should come after that. Thank you.
Thank you.
Okay, brilliant. So I think next up in our list, and we do only have time for a couple more at this stage, but next up is Camila. Camila, if you want to go ahead and unmute and ask your question.
Yes, so it's
Thanks.
more of an inspiration kind of question. I was just wondering, how do you envision a system that is to be deployed in real world? So what would the actual minimal product be? Like, how would it have to be integrated with like the real world data, like electronic health records, or like what else would be needed for it to work in practice so that practitioners could use it?
Well, Camille, I guess this is the million-dollar question. So that's a very, very good question and an important one. So the one way in which I can envision that, and we could have an entire maybe inspiration exchange as brainstorming about that, but one way to make it as a first departure from a current decision support system, but one now where not only we learn from data to make recommendations, but rather we also see the decision-making of the human, and we use methods such as Interpol, inverse bounded rationality, or if you want to do counterfactual inverse reinforcement learning, to try to really understand how the human has arrived to that decision. And when we provide a recommendation, we not only show the recommendation of the machine, but we also explain why this recommendation has been done using the mental model of that particular user as derived through one of these methodologies. So I see as a first minimal step in that direction, explain recommendations, not like currently do with some black box explanations to white box explanations, which may be very naive, but rather use this type of technology that we have built so far to explain why the recommendation was made, and maybe use that to engage the user in accepting this, or conversely not accepting this and providing feedback to the machine as to why the recommendation was wrong. That may be a first one, but again, maybe we should organize an inspiration exchange just about that.
Yeah, because I was just wondering, like, if so for example, you have like a pre-trained model from the observational data that you have and deploy it in a hospital, and then a doctor, for example, uses it, and then the system has to adapt to that doctor. As you said, it has to be like, the recommendations should be particular to that user. So like the person would have to be
Camille, unfortunately, we do not have a lot of time in this session, but let me just say, sorry to interrupt, because what you're saying is very interesting. That's the reason I said maybe we take it to another session. But you are right, there may be multiple decision makers, multiple doctors, multiple groups of maybe even patients that are making these decisions together. And there is be an opportunity to see variation in the decision making, preference being different, maybe even the rewards of these different decision makers or something else being different, and integrating these different views into the ecosystem, but also making them apparent to the decision makers. I think it's what's interesting.
Okay, so I think we have time for only 2 more questions, and these will be slightly kind of lightning round style, if that's okay. So second to last one, or next one is Max. I think you had a second question. If you just want to ask that one, please go ahead.
Okay. Thank you. Yeah, it was related to Alihan's presentation. In particular, the optimism, adaptivity, etc., the decomposition thing. Just wondering if I can interpret this structure as an extension of dimensions, or perhaps on the actions along the trajectory, in order to capture the variation of the utility functions among different people or different individuals, or do you think it is a practical or reasonable idea to do the dimensionality expansion on actions to capture the variation of the behaviors? Thank you.
I think the first interpretation is more accurate. If I were to kind of summarize the motivation behind introducing this new parameterizations in addition to the reward function, is that when you just try to learn all the dimensions of a reward function, that is simply just too much. It can easily kind of fit into any type of behavior you might have in your data. I guess the motivation here is that we kind of fix the reward function as what we consider as ideal, and we focus on only on this like 3 parameter, which severely constricts the kind of explanations you could have, and it kind of makes it both easier to identify those parameters from the data, But it also, since the amount of parameters are small, a human can look at those parameters and more readily kind of reason about it, as opposed to like seeing maybe hundreds of like free dimensions in a reward function, seeing only these 3 freedoms of variation is like more easier to digest, I guess.
Okay, thank you.
Okay, and I think for our final question, we have one from Schaar. If you want to go ahead.
Yeah, sure. Can you
Thank you.
hear me on the
Brilliant.
My question was, from what I gathered, you seem to be rather distrustful, in a sense, of the experts' own, rationalization of their actions. But couldn't it be also like interesting in some cases to include, explanations from the experts as to why they did what they did, with, of course, the additional challenge that you cannot trust them entirely because you're also trying to discover hidden biases and things like that. But would something a bit more interactive in which like you ask questions to the experts in order to get additional info from them about, for example, causalities and things like that be possible or envisioned? Or
So thank you, Charles, for the this question. I may not have been clear, but this is exactly the type of thing we envision. So what we are saying is that we would like to learn representations of thinking and of behavior and of information integration of the human, and then present it to them and ask them, is this type of model representative of their decision making? Did we forget to include something? Did this, let's say, representation that we learn through quantitative epistemology is accurate? And ask them to give feedback on that, as well as teach them to use these models to empower them. And it may be that one type of model may be very useful for one human, but not for another. So even the style and the type of representation may be part of what's provided to the human to select upon, as well as the information. So we do envision this dialogue and this feedback. That's the reason in my slide there was a feedback.
Okay, it's the feedback part, like, the back and forth that I kind of missed, in the sense that I thought it's like you see the experts' actions, you create a model based on that, and then you just give it to them so that they can meditate on it and be wiser. Or
improve themselves,
no
and improve each other. That's the reason I called it a human-machine partnership.
Okay, so I think this is probably a good time to wrap it up, especially since this is now, I think, one of our longest sessions to date, but definitely time well spent, given the amount of interest and engagement, which is fantastic. But just to give you an idea about what's coming up next. So we're going to be taking a little bit of a break and returning in September for our next Inspiration Exchange session. And we will be choosing the topic relatively soon, and we'll let you know in due course via our email list or, our Slack group. Also, this session now will be, of course, uploaded to YouTube within the next couple of days. So yeah, please do look out for that, and we'll drop you an email about that as well. Just another note, over the summer, of course, there's a lot going on, and this includes ICML, where we do have an awful lot. So there are a few things that I just wanted to point out in the hope that you can catch us there. So first is a tutorial by Mihaela, an ICML tutorial on synthetic data, which will be happening on July 19th. Details of that are on our website. We also have keynotes at 2 workshops. So, and these are by Mihaela as well. So one is the Interpretable Machine Learning for Healthcare workshop, which will be happening on July 23rd. And the other is the time series workshop, which will be happening on July 24th. And again, both of those can be found on our website if you want any details. Of course, these topics like synthetic data or time series are things that we have covered in previous Inspiration Exchange sessions as well, but these are evolving areas where we're continually doing new research and developing new methods and frameworks. So really, these are opportunities to present the absolute latest that's happening here. And we will also have poster sessions for our lab's 4 accepted papers at ICML. And again, if you do want more details, please do take a look at our website, where we'll be posting about this in a couple of days, but you can already find the info for most of these events on the events section on our website as well. In the meantime, if you do want to stay up to date with what we're planning for Inspiration Exchange, of course, we do send out our regular emails and we post into the Slack group, but you can also just visit our dedicated page for these sessions. And we would like to ask you as well to please let your friends and colleagues know about Inspiration Exchange, because we're trying to build a community, and word of mouth definitely does help us a lot. Other than that, until we see you next later this summer, please do take care of yourselves. Thank you so much for joining. Thank you for your opinions and your questions, very much appreciated. And I'm really looking forward to seeing you again next time. All right, thanks a lot, and take care and stay safe.